Hello everyone, I'm Saurabh, and today I'll talk about our paper Tuxedo Maximizing Smart Contract Computation and Proof of Work Blockchain. This is joint work with Ling Ren from UIUC and Nitin Vinay from IIT Bombay. So in Proof of Work Blockchain is a set of nodes maintain a distributed ledger where append-only distributed ledger where they add blocks, and each block has this following structure. The block points to a previous block with a previous hash. Block also contains a list of transactions, Ti, and also a state, sigma I, which is the state after executing all the transactions up to block Bi. The block also contains a nonce, which is the solution to the proof of work puzzle. Nodes append blocks to this ledger by creating new blocks where they add new transactions, update, compute new state, and also solve new proof of work puzzle, where the state sigma I plus 1 is computed on top of the previous state by executing the transactions in Ti plus 1. Here, pi is a deterministic transaction execution function. Similarly, this is the example of block I plus 2. For this paper, we have to look at the proof of work block mining procedure in slightly more detail. Let's consider at a miner. The miner has seen block Bi, and the miner also has a set of transactions, which is called the transaction pool, consisting of transactions that did not appear in any blocks up to block Bi. Then, to mine the next block, what the miner does, miner creates a new block structure that points to the previous block. Miner selects a set of transactions here, tx1 up to tx4, computes the updated state sigma I plus 1. And once all of these are complete, the miner starts proof of work. So two things can happen while the miner is trying to solve the proof of work puzzle. The first, which we refer to case 1, is that the miner successfully mines a block before others. That means the miner finds a solution to this nonce. In that case, what the miner does, miner deletes the set of transactions from the transaction pool that are already included in Ti plus 1. And then the miner starts the same procedure for block Bi plus 2. More specifically, miner selects a new set of transaction Ti plus 2, consisting of tx5, tx6 up to tx8. The miner computes a new updated state, sigma I plus 2, and then starts proof of work again. Note that here, the miner cannot start proof of work until it computes sigma I plus 2. As a result, if computing sigma I plus 2 takes tau units of time, then tau units of times are wasted because the miner is not mining proof of work, not doing proof of work for that tau units of time. There's another scenario where this gets worse, where a different miner mines a block before the miner we're looking at. In particular, let's recall that the miner is trying to solve proof of work for block Bi plus 1, consisting of transaction Ti plus 1. But let's assume that the different miner mined a different block at height Bi plus 1, consisting of a different set of transactions, Ti plus 1 prime, which is different from the original transaction that the miner picked. As a result, what will happen is that this new state, sigma I plus 1, will be different from the sigma I plus 1 computed by this miner. As a result, the miner will delete the partially created block and also reset its transaction pool. Then the miner will try to recompute, check whether the received block is valid or not. How does the miner check whether the received block is valid? Miner re-executes the transaction in Ti plus 1 prime and then checks whether it matches with this included state. If it matches, then the miner accepts the block. After accepting the block, miner deletes the corresponding transaction from the transaction pool and then proceeds to create the new block at height I plus 2. For that, the miner picks a new set of transactions, tx1, tx2, tx5, tx8, computes the updated state, sigma I plus 2, and then starts proof of work. Here, the question is, what is the delay from the time the miner received this block bi plus 1 and the time the miner starts proof of work for block bi plus 2? Note that the delay is two tau time units, where the first tau is used to validate sigma prime I plus 1, and the another tau time units are used to create this updated state. So what goes wrong if we use larger tau in Ethereum? The first consequence of using a larger tau in Ethereum is that the attackers with faster block processing or transaction execution power gets an unfair advantage. To see this more concretely, let's define a parameter C, which is defined as the ratio between attackers' processing speed by the honest node's processing speed. Then let's consider an attacker with 33% of the mining power, but has a lower C. In our paper, we saw that an attacker with 33% of the mining power, but has lower C can mine significantly more blocks in the blockchain. For example, if an attacker can instantly validate and create blocks, that is C equals to 0, then even with 33% mining power, the miner can mine up to more than 50% of the blocks in the blockchain. So we see that this gets worse with increasing tau by interval, where I is the average inter-arrival time. We also evaluate this using Ethereum, and we see that in Ethereum, this gets even worse. The red bar here is a miner with C equals to 0, and we see that the miner that controls 33% of the mining power mines about 70% of the blocks in the blockchain. Another consequence of keeping a high tau in Ethereum is that it increases the propagation delay. As a result, it increases the fork and also reduces the overall chain quality. For example, in our Ethereum evaluation, we saw that as we increase tau by I, the propagation delay increases. As a result, with increase in tau by I, the mining power utilization, which we measure as the ratio between fraction of blocks that are included in the chain by the total number of blocks mined by the miners, reduces significantly to about 70%. That means 30% of the blocks are getting wasted. So what value does Ethereum pick? We do our measurement, and we see that absolute value of tau in Ethereum is about 200 milliseconds. As a result, tau by I, which is 15 seconds on average in Ethereum, we get that Ethereum only uses 1.3% of the total time for transaction execution, that is useful work. The goal of our paper is to increase this to arbitrarily close to 100%. What's our approach? To solve this problem, we introduce something which we call delayed execution of transaction, or DET in short. This is an idea parameterized by a parameter zeta. And the idea is to report the execution result of a transaction of transactions Ti in block Bi plus zeta. In Ethereum, zeta is equals to 0, but in DET, we consider non-zero zeta. For example, let's consider zeta to be equal to 2 and then see what's the difference. So in Tuxedo with DET in Tuxedo with DET and zeta equals 2, the sigma I included in block Bi is the execution result of executing transaction in Ti minus zeta at of sigma I minus 1. Whereas in Ethereum, it was transaction Ti. If we pick a concrete parameter of zeta to be equal to 2, this is what we get. Similarly, the sigma I plus 1 in Ethereum is computed using sigma I and Ti minus 1. And same for sigma I plus 2 as well. So now let's just look at why delayed execution of transaction helps in Tuxedo. So now let's consider the case one from our earlier scenario where the miner is trying to mine block bi plus 1, which includes transaction ti plus 1 and state sigma I plus 1. Here, recall in DET, the sigma I plus 1 is computed as execution of transaction in ti minus 1 atop sigma I. Now recall with DET, with zeta equals 2, sigma I plus 2 will be the transaction execution result of executing ti atop sigma I plus 1. Now, observe that the miner already knows ti. Furthermore, miner also knows sigma I plus 1. As a result, the miner can pre-compute sigma I plus 2 in parallel with the proof of work. Moreover, the miner can also compute sigma I plus 3, which only depends on sigma I plus 2 and ti after ti plus 1 after computing sigma I plus 2. Now, if the miner successfully mines a proof of work puzzle for block bi plus 1, the miner can immediately start proof of work for block bi plus 2 because the state required in this block, sigma I plus 2, the miner has already pre-computed this here. As a result, there is no waiting time for PoW in Tuxedo. We'll also look at the case 2 where a different miner mined a block. Here, the miner is trying to solve proof of work puzzle for block bi plus 1. But instead, a different miner solved it first and sends the block to our miner. The different miner includes a different set of transactions, t prime I plus 1, which is different from the original set of transaction ti plus 1. Nevertheless, the sigma I plus 1 included in block bi plus 1 does not change because it only depends on sigma I, which is unchanged, and also ti minus 1, which is also unchanged. Moreover, sigma I plus 2 also doesn't change because it only depends on ti and sigma I plus 1, both of which remain unchanged. As a result, however, sigma I plus 3 gets changed because now ti plus 1 has been updated with t prime I plus 1. Nevertheless, the miner can immediately start proof of work for block bi plus 2 because it already has sigma I plus 2. And also in the meantime, the miner can compute updated sigma I plus 3 using the new set of transactions that it received as part of block bi plus 1. What it shows is that even in case 2, DET ensures that there is no waiting time for proof of work. But there are many challenges in making Tuxedo work. One of the important challenges is to pick zeta correctly. Because if we pick the parameter zeta to be too high, then transactions will have higher latency because they get executed only after zeta blocks. If we pick zeta to be too small, it's possible that miners will not have enough time to pre-compute the required state, and then it will introduce the waiting time. I'll strongly encourage interested people to look at our paper for suggested values of zeta. We also have other things in the paper. We show how to support transactions that require immediate validation. We also provide a mechanism to disincentivize invalid transactions. We also show that Tuxedo is as secure as original Nakamoto consensus. We also have an implementation. We implement Tuxedo atop Ethereum Get Client version 1.9.3. We evaluate this atop a distributed setting with 50 nodes that mimics the top 50 miners in Ethereum. We also have a simulated delay between these networks, which we simulate using TC-set. We test both Tuxedo and Ethereum with various smart contracts like empty loop, quicksort, matrix multiplication, etc. We also implement an adversarial miner that skips block validation and tests both Ethereum and Tuxedo. So let's recall the results that we have seen for Ethereum. We saw that in Ethereum, a miner that can instantly validate and mine blocks and only controls 33% of the mining power will mine 60% of the 70% of the blocks in Ethereum. Whereas in Tuxedo, we saw that if a miner controls 33% of the mining power, independent of C, the miner mines the same fraction of blocks which is proportional to this mining power. We also see that while in Ethereum with higher tau by I, the mining power utilization decreases, it remains same in Tuxedo. We have many more results in the paper. In summary, we provide an extensive analysis of limitations of naive increase of tau by I. We also provide a mechanism to enable arbitrary value of tau by I in proof of work blockchain. We have an implementation and extensive evaluation results in the paper. Future directions to improve or to extend Tuxedo will be to adapt Tuxedo for sharded blocks and adapt Tuxedo for BFT consensus. Thank you.